get a recording. So rates of change in tangent lines, we're discussing section 2.4. So Mrs. Blanford persuades Mr. Dioli to get a Twitter account. His handle at second most happy place. If anyone didn't know, so Mr. Dioli is very good at marketing. You know, we're called Sacred Heart Prep, SHP, second happiest place. I'm not sure if you ever got that, but he actually made that up, not just after Disneyland. It was Disneyland's is the happiest place on earth, but it stands for that. So just so you know, if anyone didn't know that, it took me about 10 years to figure that out, just so you know. But that's actually how he created that. So it's a very good marketing tool to get people to come to our campus. Anyway, he ends up with 30 followers after 3 hours and 100 after 5 hours. So one way you could think of this is think of X as time and think of Y as a number of Twitter followers. So very important that we're doing a lot of modeling. And usually we use X and Y as our variables. And we're gonna have some real life applications. And it's always good to establish this will be X, this will be Y. Typically X will be time, just so you know, that's kind of typical. And a slope, you guys should know what slope's all about. Slope is a change in Y over the change in X. Y2 minus Y1 over X2 minus X1, right? We know this. So let's take a look at this first part here. Excuse me. Just need to expand this on my other screen here. Okay, so you're asked to find the change in the number of followers from 0 to 3 hours. So initially he had nobody, right? So at X equals 0, he had no followers because he just opened his account. And the graph shows that. After 3 hours, however, it's pretty clear that Y is 30, based on the graph and based on information in the first paragraph here, right? So if you ask to find the change number of followers in that time period, that's pretty easy. It's just 30 minus 0, right? Again, number of followers is Y. You're asked to find delta Y. We use little triangles. We call it delta. That's a Greek alphabet. I'm going to use it a lot in this class. It's used often in a lot of STEM courses. They use delta as like change. A lot of your parents who might have a engineering background probably just use that in their everyday vernacular. So change in Y, change number of followers, is just going to be 30. Doing 30 minus 0. So that's easy, right? Now, the change in number of followers from 3 to 5 hours. So from 3 to 5 hours, hey Gabby, good morning. We just started, so don't worry, you're okay. We're doing the 2.4 nits, and hope your Wi-Fi will hold up.
Great, thank you.
No problem. Change number of followers in time frame from 3 to 5 hours. So at 3 hours, we still have 30 followers. At 5 hours, now he has 100 followers. So you do 100 minus 30, which is 70. So again, that's just, you're looking at the change in Y in that interval. Intervals are very important too. So again, for the first 3 hours, the change in Y is 30. Between the 3rd and 5th hours, the change was 70. Now here is the question. During which of those time periods, during the first 3 hours or between the 3rd and 5th hours, was the number of followers growing the fastest? Or sorry, a number of followers growing faster? I'm only comparing two intervals. You should say faster, not fastest. That's grammar, right? So that's what we're trying to figure out. So what you need to do is determine slope, because slope represents a rate of change. You want to see what interval has the fastest change. Was it the first interval or the second interval? So here's how you could look at this. We have to look at this through the lens of slope. So we'll answer this question, I think you could probably tell it's going to be the second interval, but let's prove it, right? So one way to see this, Mr. Dioli is accumulating followers in the first 3 hours at a rate of 30 Let me change the colors for a bit of contrast. 30 minus 0 over 3 minus 0. All I'm doing is calculating the slope for the first 3 hours, or I'm finding the slope of this line. Kind of a crappy looking line. I'm trying to find the slope of that line. Well, how far did I rise? 30. How far did I run? 3. Or just more mechanically, 30 minus 0 over 3 minus 0. y2 minus y1 over x2 minus x1. 30 over 3 is 10. Pretty easy, right? I do care about units. Actually, I'm going to be extremely picky about units. The AP is. This is just the way it works. You got to understand context what you're doing. We're finding followers per hour, right? Followers per hour. So 10 followers per hour. So that's the rate. Now for the next 2 hours, between the third and fifth hours, what was that rate? That rate would be, remember at x equals 5, y is 100. So guess what? I'm doing 100 minus 30, or 5 minus 3. So in that time period, he increased the change. Increase, right? The change was 70 over 2 hours, or 35 followers per hour. So it's pretty clear that which time period grew the fastest, that one, 3 to 5. 3 to 5 had the had a faster change than from 0 to 3 hours. Now the way we formally classify what we just computed is called an average rate of change. Actually, let me get a highlighter out, it's probably better. So on the AP, they love using this phrase and asking you to find this stuff. And you don't want to confuse it with other rates of change, which we're going to talk about other rates of change later. But average rate of change is exactly what it means. On average, how did our quantity that we're measuring, what are quantity, in this case, number of Twitter followers, change over a certain time period? So I'm just going to repeat. I'll just compute it up above. For the first 3 hours, ten followers per hour. For here, 35 followers per hour. And I'm just getting lazy. Put a double quotation to repeat the units up above. So we call this an average rate of change. I am going to kind of talk about a different example in just a little bit. But don't want to get us too off track. Any questions so far? What we just did. We're okay?
Mr. E,
Good.
could you have a negative rate of change?
Totally. Absolutely. Yes. Great. Fantastic question. I should have brought that up. Yes, totally. Now, again, it depends on what you're dealing with, right? Like, well, with money, you could lose money, right? If you're looking at like how much profit or loss you might have over time period, that's actually a great way. If you're looking at anyone who's in economics or likes to study the stock market, this is a lot of fun. Like those who are going to do econ in college, which is a fantastic major, you do calculus like crazy. Of course, in science, like for example, velocity can be negative, right? Because you go in the opposite direction. Absolutely, you can have negative change. Say, for example, I want to look at like how quickly my daughter is growing. I could do that actually. That might be kind of fun because we actually do that. Maybe I put that as a word problem on a test or something. Like, my daughter was this tall at 6 months old. Now she's this tall at 10 months old. What was her average rate of change of height? Is she going to shrink? I hope not. So So, I mean, yeah, some things you can't see negative, but it just depends on the context, what you're dealing with. Can Mr. Dioli lose Twitter followers? Sure, absolutely. I mean, that happens all the time with social media. People can lose followers too, but typically usually gain. Okay, so let me clear screen. So let me kind of talk about this middle part. And before we do example one, let me kind of talk about another kind of relevant example about rate of change, and then we'll do example one. So in the middle here, although average rate of change are very often measured in units, they'll be per hour, per minute, or per some unit time. They don't have to be, just so you know. For those who are familiar with Twitter, it's something called retweets, right? So like, for example, say I tweet something and one of my followers likes it, he or she could retweet it and have it to their followers, right? Maybe they think, oh wow, this is a really cool thing that, Gus just said. I want to share that with other people, right? And of course, that's what makes Twitter such an exponential kind of thing, right? So for example, Mr. Dioli gets 4,000 retweets from his first 4 tweets, right? So he tweets and then there's 4,000 retweets from those 4 tweets. So the average rate of change of retweets, we write as this: 4,000 minus 0 over 4 minus 0. So basically what's happening is that my x is to mean the number of tweets from Dioli. The y is to mean the number of retweets from his followers. Sorry, Betsy handwriting. Number of retweets. So you could kind of measure and say, well, every time Mr. Dioli sends one tweet, on average, he gets 1,000 retweets, because that's what works out over here. 4,000 over 4. By the way, I think Mrs. Blanford used Twitter because her son used to work at Twitter. He worked there right in the beginning, so I'm guessing he's done pretty well. So 1,000 retweets per tweet, or per Dioli tweet, we'll call it that. So so you don't always have to be dividing by time, just so you know. It's a rate of change. When you're comparing 2 quantities and you just want to see how much something changes per something else. Per means division, right? So for example, initially, Dioli opens his account, hasn't sent any tweets yet. Of course, doesn't have any retweets, right? What's a retweet if he doesn't tweet? He tweets 4 times, all of a sudden, he gets 4,000. Now, would you guys say with confidence this is a linear function, or could it have done a lot of other wacky stuff along the way? Could we assume that it was linear? No. It could have been, maybe. Maybe when he sent one tweet, he waited kind of a few minutes and, oh, we got 1,000 retweets, sorry. Then he sent another tweet a little while later, and it waits kind of a few minutes and like, oh, okay, I got another 1,000 retweets. Probably didn't work that way. Maybe he sent one tweet that was just kind of like, like maybe just like talk about, what he did over the weekend. And then he says, oh, school's gonna reopen. He gets a bunch of retweets, right? Maybe from a bunch of parents and students. So you don't know, right? That's why we call this an average rate of change. On average, how did this change given the units? So an average rate of change basically can be defined as this, and it's really simple. F of B minus F of A over B minus A. It's purely slope. That's all you're doing. It's just slope. And it's basically the amount of change in Y over the length of your interval, which we label as X. And your interval could be time usually. In this case, it was, number of tweets. It just depends, what you're working with. So before I do example 1, and then I'll have you guys do example 2 in breakout rooms. Excuse me. Let me share a whiteboard. And let's say you're driving from here to San Diego. I went to school at UC San Diego, so I did that drive a lot. So let me put in my current location in Redwood City and UCSD. And by the way, if anyone's applying there and want to know more about the campus, more than happy to help you. Of course, it's changed a lot since I graduated in '99, so it's been, and I haven't visited in about 10 years, but anyway. Let's see, let me go to the Visitor Information Center. Okay, so it says about 470 miles, and it'll take me about 7.5 hours. I want to take the scenic route, take me 8.5 hours, but it's okay, we'll take Highway 5. Okay, so from RWC, where I am right now, to UCSD, it's 470 miles. Actually, it says 470 miles, we'll say 470 miles. And it says it'll take me 7.5 hours. So on average, I travel 470 miles or 7.5 hours. Because right now, I'm sitting here in this room. I haven't gone anywhere. But once I get in my car, I'm just going to drive the Highway 101 first and catch Highway 5 through some other freeways. And then and 5 actually takes you all the way through. But if you ever drive through LA, by the way, don't take 5. I know some of the shortcuts. So just ask. I'm more than happy to tell you. But anyway, but everyone's also working through at home through the pandemic, so maybe there's not free. Anyway, I digress. So 470, hold on, 470 divided by 7.5. It's about 62.67 miles per hour. So by the way, this is an average rate of change. Now let me ask this question. Do you think I would drive at that speed the entire time through my trip? No, absolutely not. Do you think when I get to Highway 5, when it's kind of open highway and it's absolutely nothing, you're driving to the middle of nowhere, am I going to be tempted to hit 80, 90 miles, maybe 100 miles per hour? Probably. Be safe. I think once you get to 100, gets a little scary. But a lot of people drive 80, 90 miles, and people do so safely as long as the road conditions are dry and there's not heavy traffic. In fact, I think the speed limit's even 75, and if you go 80, cops won't pull you over. But once you hit 90, then you're asking for trouble. But so those are called instantaneous rates of change. Like maybe for that one stretch in between here and LA, I'm going really fast. Then let's say all of a sudden I have to stop for food or gas, because you do have to do that, or use the bathroom. Then all of a sudden my speed's going to slow down, right? Because I got to hit the brakes, get off the freeway, maybe drive to like Chick-fil-A or In-N-Out, whatever, and then get back on the freeway again. Or maybe there's traffic, maybe there's an accident or something, or maybe it starts raining and I have to hit the brakes. So we're going to talk about that on the next page in just a little bit. But that's just something to keep in mind, like, the distance from here to here, I have an average rate of change, but I don't drive that way the whole time. Maybe a good chunk I might if you hit the cruise control, but anyways, I think it's just really fascinating stuff. So sorry for my digressions. Okay, now let's talk about example 1. Then I'll have you guys do example 2 in breakout rooms. Then we're gonna do this little demo over here, and then we'll see how example 3 goes. I think we can get to at least the first 3 pages today. So example 1 should be pretty straightforward. Here you got a function, and you're asked to find the average rate of change over a certain interval. And again, just to repeat, all we're doing is this: f of b minus f of a over b minus a. So examples 1 and 2 are pretty boring problems. Just find the slope, that's all. So all you're going to do is you're going to do f of 12 minus f of 4 over 12 minus 4. That's it. Of course, f of 12, you should know your function notation. Just means ln of 12, whatever that is. minus ln of 4, whatever that is, over 8. And if I were to work that out, you can give us a decimal, I don't really care. If you remember your log properties, you can actually combine these two. Remember, when you're subtracting two logs of the same base, you can condense as a single log using the quotient property. And of course, it's ln3. We know this. I don't have my graphing calculator in a different room, and I'm too lazy to get up right now. So we'll leave it like this. That's fine. I don't care if you leave it like that. And we don't know what the units are, so we don't worry about units. It's not a word problem, so don't worry about units. That's it, right? That's all we're doing. Okay. Actually, maybe we won't, because this will be really fast. Maybe we won't do a breakout room. Just go ahead and do example 2. I'll give you guys 2 minutes. Tell me what you get. Actually, we'll do this. Send it as a private chat to me once you have example 2. So send your answer as a private chat for example 2 once you have it computed. Okay, so I see about 9 chats. That's good. Yeah, 4, good. Awesome. Yeah, it should be 4, all you're doing. There's more coming in, great. Thank you guys for contributing to that. So really simple, f of 2 minus f of negative 2. Now, if you got 0, you made a careless mistake. That's a common error. I'll show you how you probably got that. So f of 2 is easy, that's 2 cubed. Minus negative 2 cubed. A lot of negatives going on there, so be careful. 2 minus negative 2, of course, is 4. You have 8 minus negative 8, right? Because negative 2 cubed, negative 2, negative 2, negative 2, that's negative 8. But there's another minus, so minus negative 8 is plus 8. And 6 over 4 is, of course, 4. Good. And thank you for those who just brought chats in. Great, thank you so much. So good, easy, right? So what does this formula remind you of? I already said so. Reminds you of slope. And more specifically, we call it the slope of a secant line, which is a nice segue to what we're going to talk about on page 2. So we call it the slope of a secant line. And if I draw this in black, so here's f of a, here's f of b. And the slope of that line is called this is called a secant line. A secant line is a line that passes through 2 points of a curve. So a secant line, in case you may have forgotten, I'm not sure when that's covered in geometry, but a secant line is a line through 2 points on a curve. By the way, your curve could be continuous, could not be continuous. That's something we're going to explore also, and then kind of work our way towards these more advanced calculus principles down the road. But yeah, that's all it is. Okay, any questions before we move on to page 2? All right, so I'm clear. Okay, now this is kind of a big one. Give me 1 second here. Let me pull it up on my end. Okay. 1 sec. Hold on. There we go. Perfect. All right. So what do we have going on here? We have y equals x squared. And the point 1, comma 1. Now this is extremely messy way to look. So let me do this. Let me get a red marker. Actually, we highlight it. So that is this right here. Okay. So that's a parabola. What's happening is I have these tangent lines. So PQ1. So you see P is right here. And it's 1, comma 1, as I said so. But PQ1, PQ2, PQ3, we'll do PQ4, PQ5, PQ6, so forth. Those are going to be called secant lines. Okay. Their lines are going through 2 points in a curve. And Q1, you can see is 7, comma 49. Q2 is 5, comma 25. Q3 is 3, comma 9. And these are all points on the parabola, right? Like by plugging in 7 squared is 49. 5 squared is 25. 3 squared is 9. And so forth. And what we're going to do, excuse me, is we're going to investigate what happens when Q gets closer to P. That's the question we're going to answer. That's kind of the big idea here. Now, this we call a secant, just so you know. So this does come from geometry, and that's called a tangent. So here this touches at 1 point. Here, the secant touches the circle at 2 points. So that's where that terminology comes from, just so you know. Just so from geometry. So again, we're looking at secant lines, and we're ultimately going to look at tangent lines. Now, very, very simple demonstration, but it's going to lead us to a very big idea at the bottom of this page here. Okay, let me clear. What we're going to do is we're going to compute the slope of point P and all these different points here. So, and these are secant lines, right? Remember, here's the curve. Y equals x squared. Sorry, looking at point P. Which is 1, comma 1. And point Q whatever, will be somewhere in the curve here. So first step, we're just going to do 49 minus 7, sorry, minus 1 over 7 minus 1. So all we're doing is find the slope between 1, comma 1 and 749. That should be really easy. That's just 8. Which kind of makes sense, right? If I were to draw such a slope, well, okay, well, you get the point. It's just, you know, it's pretty steep. Then we're actually going to do this for all these other points here. By the way, if you plug in 1.5, remember, y equals x squared. So if you plug in 1.5, you get 2.25. If you plug in 1.3 for x, you get 1.69. If you plug in 1.1, you get 1.21. Plug in 1.01, you get 1.0201. Just use the calculator. So what I want you to do now is calculate 6 more slopes. The slope between 525 and 11, the slope between 39 and 11, the slope between 1.5, 2.25, 11, 1.3, 1.69, 11, and so forth. And what I want you to establish is a question down below. Does the slope period have a limiting value as Q approaches P? If so, what is it? So go ahead and just calculate 6 more slopes. And in a private chat, what is the slope approaching? So just take a couple minutes to do that. And tell me what it's approaching. As you get closer and closer, as point P and Q start getting closer together. Okay, I see some coming in the chat now. Okay. Good, most of you guys are saying 2. That's good. You should be getting something close to 2. I'll kind of tell you the slopes because I haven't calculated on my other screen here. 6, 4, 2.5, 2.3, 2.1, 2.01. So we notice is that as Q gets closer and closer to P, the slope gets closer and closer to 2. This can lead to a big idea in just a second. So those are the slopes you should be getting. 8, 6, 4, 2.5, 2.3, 2.1, 2.01. So does this slope appear to have a limiting value as Q approaches P? And what happens is that when Q and P coincide, our line is now tangent to y equals x squared at 1, 1. When this happens, we call this an instantaneous rate of change. Because now you know how fast you're moving at a point. For example, if I'm driving from here to San Diego, maybe when I'm passing through, I can't remember those towns anymore, I've done drive a long time, but maybe when I'm driving through like a particular town, I'm going 9 miles per hour. So like maybe at time t equals 2.5, when I'm on the road when I've been on the road for 2.5 hours, how fast am I going at that moment? That's what this is going to tell us. And this is something that we call this a derivative, which is going to be the whole essence again of the first semester of this course. And we think of it as a limiting case. This limiting value, of course, if it exists, because limits may not exist, is called the slope of the curve at P, or the tangent to the curve at P, and is aligned through P with the slope. So it's this tangent line. So we're really focusing on tangent lines here. That's the ultimate goal here. When we treat it as a limiting case, when the 2 points get closer and closer together. Coincide means same point. That's what I mean. When it becomes the same point. So, like, because you notice how Q is getting closer and closer to P, ultimately they're going to be the same thing. Now, when they become the same thing, there's a problem. If you calculate the slope, you can get 0 over 0. But we saw that off-limit limits, right? And we had all these different techniques. We're going to get there, probably in 3.1 next week. For now, we're just taking more of a coordinate geometry approach. So let's look at example 3 here. Let's find the slope of the curve at y equals x squared, the point 1, 1, in the equation of the tangent line at this point. Okay, so here's how we're going to do it. So here's the curve y equals x squared, here's 1, 1. And on point Q, and it's going to be kind of weird, we're going to call it that. I know it's kind of strange. Point Q, we're going to call 1 plus h for x. And because it's y equals x squared, your y value is going to be whatever x is squared. It's because x is 1 plus h, my y would be 1 plus h squared. I know it's kind of weird. And why am I doing it this way? I'm doing it this way, so this is at 1. This is at 1 plus h. The horizontal distance between P and Q is h. Sometimes we say this, delta x equals h. Delta x is a change in x, so we're deliberately calling the change in x h. Why that letter? I don't know. I don't know the history behind this, but a lot of calculus teachers and those who've are the pioneers of calculus use that letter. I don't know. But h is going to purely be the horizontal distance between P and Q. So for example, it's just a way to generalize it, I guess. So like what if h were 2, for example? Then the x coordinate point Q would be 3, because the distance between those two is 2. Or if h is like 10. If h is 10, then the x coordinate point Q would be 11. Of course, we want h to be tiny, because we want P and Q to be close together. So that's what we ultimately want. We're going to try to make h small. That's what we're going to try to accomplish here. Why? So that Q approaches P. Okay. Now h, just so you know, right now I have h being a positive value because obviously Q is to the right of P. It doesn't have to be. It could be negative. I could have done this, generally speaking. Here's my point I'm interested in. Call that 1. I still could call this 1 plus h over here. Just h happens to be a negative value because I'm going to the left. So h could be positive or negative, just so you know. Now, the slope of a PQ. And we do some blue for a bit of contrast, or we'll do green. So remember, change in y or change in x. So 1 plus h squared minus 1 over 1 plus h minus 1. Now, if you were to work that out, you would get this. 1 plus 2h plus h squared minus 1 all over 1 plus h minus 1. Now, will things cancel? Absolutely. These will cancel, and these will cancel. So what am I stuck with? Two h plus h squared over h. There's a lot of symbolic stuff. It's just what we have to do. Can I simplify further? Sure. Pull on h, 2 plus h. And you have h down below. Can I cross this off? Absolutely. So now we get 2 plus h. Now, this is going to be a big part coming up next, but any questions so far about what I've done, about the algebra, what we're trying to do here? Again, just to recap, we have y equals x squared with a 0.11, and we want to find the equation of the tangent line at 1, 1, meaning that, if I have this curve, and I want a line that, I want the equation of that line. That's what I'm looking for. And the slope. I want the slope of this line, and I want the equation of that line. In order to do that, we make up a point called Q, 1 plus h squared. H is some number that represents a horizontal distance between P and Q, right? It was just this right here. H could be positive or negative, as I mentioned before. And what we're trying to do is we're trying to make h small. We're going to do that in just a sec. But initially, I just calculate the slope using all my algebra skills that I know. And to find the slope, you treat it as a limit. So what you do is you take the limit as h approaches 0 of your expression. Remember what this represented. It represented that. All this right here, 2 plus h, was the slope between those 2 points. Remember, we want the limit of the slope of the secant line as q approaches p. Remember, here's a line again. Sorry, here's a curve again. There's point P. There's point Q. If I want Q to get closer to P, as Q approaches P, H approaches 0. Right? H gets smaller as we do that. So we choose a limiting case. And of course, it's pretty easy. 2 plus 0, that's just 2. So the slope of the tangent line is 2. And we actually computed that on the previous page. Slope of the tangent line at 1, 1 for y equals x squared. That's what I just computed. The slope of the tangent at 1, 1 for y equals x squared. So the equation of the tangent line will be this. By the way, leave it in point slope form. On the AP, they do not care if you go to slope and intercept form. In fact, I advise you to not do that. Because if you make a mistake when you're moving things around and you get the wrong answer, you get nothing for your work, for a good chunk of your work. So please, please, please just leave it in point slope form. It's actually the preferred technique for this course. Remember point slope formula? Hopefully you guys didn't forget that. If you did, it's just this. Remember x1 and y1 are the point that we're looking at. We're looking at the point 1, 1. M is of course a slope, which we saw is 2. So this is what we're doing. We're working our way towards calculating slope using limits. This right here is the whole essence of first semester college calculus, the slope of the curve. The limit as h approaches 0 of f of a plus h minus f of a all over h, where you're trying to find the slope of the curve or the tangent line at a comma f of a. And just so you know, that's a change in y. That's a change in x. Remember, you have 2 points here. You have this right here and this right here. A comma f of a is point P. A plus h comma a of f of a plus h. Now remember, I let a be 1 in this problem. So we have 1 comma f of 1. And then we have 1 plus h and f of 1 plus h. The bottom is going to always simplify to h because you're subtracting these two x values. You know, I mean, you have here I have 1 plus h minus 1. Whatever a is, that's your x coordinate of your point of tangency. You know, that's going to cancel anyway. There's a question in the chat. Please ask questions because this is a big moment here for our class. So the question is, so limit of slope of secant line PQ equals, yes, Eleanor definitely did a great job summing this up. She wrote, so does the limit of the slope of the secant line of PQ equal the slope of the tangent line slash derivative? Yes, when Q and P are getting close together. Let me actually see if I can. Is there a way I could just do a text? Yeah, let me put a text box here. There we go. Should do more often in Zoom. So limit of slope of secant line at PQ equals, and I'll type this in red. Well, yes, as long as Q is getting closer to P. Yes, that is in essence what we've done today. The limit of the slope of the secant line equals slope of the tangent line as long as Q is getting closer to P. Yes. And we call this the tangent to the curve at P as well, because that is what you're doing. Any questions? Nope, okay. Let's keep moving. Another thing we have to talk about too will be the normal line. The normal line means a line that's perpendicular to the tangent line. For those who are taking physics, you might have learned about normal forces. That's like a force that's perpendicular to your motion. So normal means, in the world of math, means perpendicular. So again, here we have a curve, y equals x squared, which again, why am I drawing it incorrectly? So the red line is tangent. The blue line is called normal. Now the normal will cross the graph in another place as well, but it's one that's perpendicular to the tangent line. So example 4 kind of has that discussion. I think, looking at time, because I did promise I wanted to end this a little early so you guys can have a little bit of a break. Let me kind of at least kind of set it up just a little bit, and then if you guys want to work through it, you can. Just so you know, the filled out notes are all in Schoology. So if you want to actually do the other three examples, if you so desire, you can. I am going to make a video, however, on examples 4, 5, 6. So you guys can watch that. And then there'll be a Google form that goes with that. And there'll be some textbook problems. In all likelihood, I probably won't do a worksheet this weekend. Probably just some textbook problems and then video and Google form. That'll be the homework. That'll be due Tuesday. And no discussion this week, by the way. I'm not doing a discussion this week. Again, you guys have a lot going on with the test. So, and I know college apps and SAT, ACT is coming up. So want to be mindful about that. But of course, we still have to do work, right? So I'm not going to bombard you with too much stuff over the weekend. So anyway, let me just quickly set this up here. So you have to find the slope of the curve at x equals 2. So what you're going to do for part A is find the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. Now, if you want, you could write this. If you want, you could do that. I mean, but it becomes redundant after a while. Just write h, because you know it's going to be h on the bottom anyway. And I give a big sigh because you have to do this. 2 plus h cubed minus 2 times 2 plus h. All that is all this. And then, of course, you got to do this part right here. That's 2 cubed minus 2 times 2. And of course, the whole thing all over h. And don't be lazy, write the limit notation. And then you have to kind of go through the motions and go through all the algebra. I'm not going to do that because in the interest of time, I want to give you guys a break. Once you do that, then B and C should be pretty straightforward. Then there's a bunch of algebra, right? For the rest of part A. For part B, remember you're doing this. And we know x1, y1. Will be 2, 8. I think that's pretty obvious. And m will be your answer for part A. Where do we get for part A? That's your m. And then for C, do the same thing. C, do the same thing, but what's the perpendicular slope? You guys remember how to find that?
Negative reciprocal.
Yep, absolutely. You did negative 1 over m. What do we get for A? Just flip it over and make it negative. So that's, and homework's gonna be a lot like that. So you guys are getting that practice. Example 5 and example 6. We'll kind of follow somewhat the same stuff. Now, for those who've had pre-cal BC honors, you're going to know that there's a shortcut. There is a way you can actually do this pretty easy. Like I know looking at this right now, the answer is going to be 10. I can do it in my head. There's a shortcut. I'm not going to tell you what that shortcut is until much later. If you could always look it up, you could ask a friend, but I want you to do it this way though. There is a way that you can do this whole process like it's a matter of seconds. But you have to understand the algebra, the numerical, and the graphical aspects of all this. A lot of people don't do this and they just kind of go straight to the shortcut, and then when they get to more complex stuff, they get lost. You have to understand what's happening conceptually here. So I'm forcing you guys to go through this through brute force, unfortunately. So just put up with it, you'll be okay. But yes, there's a shortcut and you guys will be cursing me after that. So, or maybe not. Okay. All right, I think we're good. So we'll end a little early, give you guys a little bit of break. I'll give you guys a lot of content for today. I'm actually glad I didn't assign anything due today. I think it's just good that we just start fresh, some notes, clean slate. And yeah, tests, tomorrow's gonna be kind of my big day for grading. I should have things updated hopefully by Saturday. So, and if you have any, and then we could talk next week about your tests if you like. All right, well, I'll see you guys then on Tuesday next week. If you want to come in office hours tomorrow, I am available, just so you know. So, all right, see you guys.
Thank you.
Thank you, Mr.
Yep.
E.
Thank you.
Mr. E, can I ask a question?
Yes, I just saw your mom's email.
I didn't know until today.
You have a
and
doctor's appointment?
Yeah, they can't confirm it until 1. I don't know
Okay.
if it's COVID or something, so I don't know if I should just take it later in the day or tomorrow.
Let's just do tomorrow. That's fine.
Okay.
Yeah. Let me look at my. What? Do you have any frees at all, or what's your schedule like tomorrow?
Yeah. E and
E and
F
F.
are free, and then I'm free after school too. So.
Let's do EF. Let's see. Let me throw anything. Office hours goes 15:55. Do you want to do 9 till we had planned doing that yesterday. Just want to do 9 to
Yeah.
11 tomorrow. Let's do that.
Yeah, that's
Yeah,
perfect.
I'll
Sorry
update.
about that.
I'll update the calendar. No, you're good. Don't worry. I'll
Thank
update the calendar right now.
Okay.
Yeah, actually, I have you down for after school. Let's move that to October 2nd, 9 to 11 a.m. Just so I have a reminder. Okay, we're all set.
Perfect. Thank you so much. See you
No
tomorrow.
problem. See you. Bye.
Bye.